Yeah, we can hear you fine.
Perfect. Okay. Let me start then. Okay. Sorry that I was not able to be there with you in presence, but thank you for giving me the opportunity to talk about the Spritz code. The Spritz code has been developed over the years in collaboration
We're
with.
asking if it's just locked on him.
I was just going to move that out of the way of the slides. So,
Okay, I hear some background from the room, but okay, so we'll say the code has been developed in collaboration with Riccardo Ciolti, Federico Cipolletta, Lorenzo Ronci, which is now at RIT, Edoardo Giangrandi, Beatrice Giudici, Jake Renani, which is also at RIT. This is why I highlighted them in red, Wolfgang Castaun, and Lorenzo Sala. The code is publicly available on Zenodo. So Jay, Mosta, Carlos Palenzuela, and others have already described the importance of doing a generalistic magnetodynamic simulation. So I'm not going to add more into this. I just showing some pictures from a simulation we've done with code so that make use of the Einstein toolkit. So you have a simulation of accretion flows, also binary pellicle mergers, simulation of binary neutron star mergers, neutron star black hole mergers, supernova explosions, and so on. In all these scenarios, the equation that you evolve are the equation of generalistic magnetodynamics. Jay presented this equation in his talk in Monday, so I'm not going to say much about this, just to highlight that we consider a perfect fluid, so we ignore viscosity and heat transfer. And we also consider the ideal MHD approximation, which means that we only evolve the magnetic field. So this equation corresponds essentially to the evolutionary equation for the magnetic field, including the divergence of the equal to 0 condition. And as done in many codes, these equations are casted in a flux conservative form, in which you have the derivative with respect to time of conserved variable plus the divergence of a flux equal a source term. So when we started working with the Spritz code, this was the situation essentially with the public available codes or codes that were accessible to us and that were using the Einstein toolkit. So within the Einstein toolkit, you have gyrohydro. Gyrohydro includes the evolution of the magnetic field, both using methods that we'll describe later, like constraint transport or divergence cleaning, or evolving the vector potential itself. The vector potential formulation that was in gyrohydro used a formulation in which the vector potential was not staggered. I will say something more about this later. Gyrohydro fully support ideal fluid equation of state, piecewise polytropic equation of state, as well as tabulated equation of state. The version inside the Einstein toolkit doesn't include the support for neutrinos, but this can be easily added. Then there is another code which is now part of the Einstein toolkit, is GermHD. This also includes the evolution of the magnetic field, via the vector potential formulation, and the vector potential is staggered. As I said, I will say more about this later. When we started working on Spritz, Illinois GermHD only supported the ideal fluid equation of state. Only recently, thanks to the work of Leo Werner and collaborators, the code also includes now the piecewise polytropic equation of state, tabulated equation of state, and neutrinos. But when we started working with Spritz, this part was missing. Then there is Whiskey TSC. It's not part of the Einstein toolkit, but it's publicly available and it uses the Einstein toolkit. This code is quite advanced from the point of view of the numerical methods. It can include tabulated equation of state, it includes neutrino, but doesn't have any support for magnetic field. Then there was Whiskey MHD, which is the code that I developed over the year. This code was not publicly available, but it was using the Einstein toolkit. It included the evolution of the magnetic field via constraint transfer or by evolving the vector potential itself. The vector potential was not staggered, and for the equation of state, it only supported ideal fluid and piecewise polytropic equation of state. There was no support for tabulated equation of state or neutrino. So the idea with the Spritz was to have a code that was able to evolve both magnetic field and hydrodynamic equations, including the effect of tabulated equation of state, final temperature tabulated equation of state, and neutrinos. So the code, as I said, is publicly available on Zenodo. It's based on the Einstein toolkit infrastructure. As many of the codes that I mentioned before, use the Valencia formulation, which is essentially a way to rewrite the equation of relativistic magnetodynamics in a flux conservative form. It uses a staggered vector potential formulation. simulations. And regarding the neutrino, what we are doing at the moment is just to use a public available term called Zelmani, which include just a very simple leakage scheme. In the future, we plan to implement some more advanced scheme, like the M1 scheme that was mentioned yesterday by François Foucault. The code can reach fifth order convergence, and we are currently using that for neutron star simulations. The code has been tested on a different scenario, different both in special and general relativity. In 1D was tested, of course, with the standard Riemann problems. In 2D was tested with a cylindrical explosion, magnetic rotor test, loop advection test. In full 3D has been tested in spherical explosion, as well as the standard simulation of a stable and unstable Tolman-Oppenheimer-Volkow solution, as well as rotating neutron star. So in the case of stable model, you just study the oscillation of the neutron star. In the stable model, we study the collapse of black hole. And there have also been some tests in the context of accretion disk around black holes. So for example, this from the first Spritz paper, this was Cipolletta et al. 2020. These are just some results for the oscillation of a magnetized neutron star, spherically symmetric neutron star. On the left, you have the distribution of the magnetic field on the XZ plane. In white, you have the magnetic field lines. And this red line here is the surface of the neutron star. These are the initial conditions. On the right panel, you have the evolution, for example, the mass density at the center normalized by its initial value. And you see that by increasing the resolution, going from low resolution to medium resolution to high resolution, the models get closer and closer to the initial configuration. Okay, so the oscillation are smaller and smaller as expected. And at the bottom, you have the evolution of the maximum of the magnetic field. And again, with the high resolution, the magnetic field, the maximum magnetic field stays more constant with respect to the lower resolution case. This is another picture I'd like to show that the code can reach fifth order convergence. This was due to the work of Beatrice Giudici, which implemented Windows Z reconstruction, which is a fifth order construction, coupled with an high order by a different scheme to compute the fluxes, which is something that is implemented in other code. For example, was implementing the eco code by the Zane collaborator. It's also used in a modified version Illinois GMHD by Elias Most and collaborator. The implementation at the moment regards only the hydrodynamic quantities, not the MHD quantities. So fifth order convergence is reached only in the absence of magnetic field. What you have here on the left is a plot showing the order convergence as a function of time for a test which is called a simple wave test. Essentially, the initial configuration of the plasma is smooth, and therefore the code is fifth order convergent. Then you start to lose the fifth order convergence because in this test, discontinuities start to appear later during the evolution. So when the shock starts to appear, the method goes to first order convergence. The different lines have different methods. In particular, they're all using the Windows Z for the construction, but different order for the computation of the fluxes. So for example, in the blue line, you have Windows Z plus a standard second order HLE for computing the fluxes. In this case, the order of convergence is limited by the computation of the fluxes. Then when you start to use a fourth order HLE, you go to fourth order. When you start using a sixth order HLE, at this point, your convergence is limited by the Windows Z, which is a fifth order. And so you get fifth order convergence. Of course, in order to have fifth order conversion, you also need to use a high order Roncoulter method. In this case, we use a fifth order Roncoulter method to reach fifth order convergence. As I said, this at the moment is only implemented for the hydro quantities. So we don't have fifth order convergence for magnetized scenario. The reason for having this very high order, well, very high, with this high order of convergence, so fifth order instead of the standard second order scheme, has some application. For example, this is a test when we consider the oscillation of a stable neutron star. And for example, the green line, dashed line, is the power, represents power spectral density for the oscillation of the star when evolved with the fifth order method. And where one can really clearly see not just the fundamental mode of oscillation, but also the eigenmodes. While, for example, the standard second order method, which will be, let's say, the blue dashed line, only show the fundamental modes, but doesn't show very well the overtones. So something that I want to spend some time talking about is the problem about the divergence of B and how to deal with this. So over the years, several numerical techniques have been developed in order to prevent the formation of magnetic monopoles. Probably the oldest one is the constraint transport scheme that was first discussed by in 1966. And this essentially is a way to recast the evolution equation for the magnetic field in order to guarantee that the divergence of B stay constant in time. So it means if your initial data have a divergence of the magnetic field is equal to 0, then it's going to stay 0 for the rest of the simulation. The problem with constraint transport is that it's very difficult to implement it when you have an adaptive mesh refinement code. Because when you use adaptive mesh refinement, typically you do some interpolations. In carpet, for example, you have the prolongation and restriction operators. And therefore, you need the interpolation operators at the boundary between refinement levels that guarantee that the divergence of B is not violated. And these are quite complicated to be implemented. A code that uses the constraint transport with the correct interpolation schemes for mesh refinement is, for example, the code by Masaru Shibata. He does that. But as far as I know, these interpolator operators that preserve the divergence of B are not available, for example, in carpet. Another scheme that was developed over the years is the hyperbolic divergence cleaning method. And this instead modifies your system of equation by adding a new variable, such that essentially, let's say, you evolve also the divergence of B. So whenever you have the creation of monopoles, so violation of divergence of B, these violations are vectored out of the grid and also dumped down. A third formulation, which is the one that we use in Spritz and is also used in Illinois GRMT, is the formulation in which instead of evolving directly the magnetic field, which is what is done by method 1, 2, you evolve the vector potential. And therefore, by computing the magnetic field from the curl of the vector potential, you, by construction, get a magnetic field that has a 0 divergence. When evolving the vector potential, of course, you have the gauge freedom. You can choose any gauge. And the gauge that is typically used is called the generalized Lorentz gauge that is introduced in the paper by Etienne and collaborator and Paris and collaborator. So in this case, what you do, you evolve the vector potential in the generalized Lorentz gauge, which is given by this first equation. I remind you that the Lorentz gauge just said that the fourth divergence of the vector potential is equal to 0. In the generalized Lorentz gauge, instead of setting the fourth divergence of the vector potential equal to 0, you set equal to psi, which is a parameter that in numerical simulation is typically set proportional, inversely proportional to the time step, times n, which is the normal to the other hypersurfaces, and the vector potential itself. So this is the gauge that, for example, we use in Spritz, and is also used in Illinois GRMT. More details about the importance of using this gauge can be found in the paper by Etienne that I mentioned before. Once you evolve the vector potential, you compute the magnetic field by just taking the curl of the vector potential. And therefore, your magnetic field is by construction of divergenceless. Here at the bottom, I wrote the equation for the evolution of the vector potential. This one comes directly from the evolution equation of the magnetic field. Okay, so the derivative of the magnetic field with respect to time equal minus the curl of the electric field. The electric field is E. And the bottom one is the evolution for the scalar potential, phi, which is instead comes directly from the gauge condition. Okay. Alpha is the lapse function, beta is the shift vector, and gamma is the determinant of the trimetric as usual. So these are the equations that we solve with Spritz, and these are the same equations that are also evolved in the Illinois GRMT. So first of all, what does it mean a staggered formulation? A staggered formulation means that the vector potential is not stored in the same points where also the other quantities are stored. So in this diagram that you can find in the Cipolletta paper, 2020, we have that the hydro variables, for example, the rest mass density, the velocity, the pressure are all stored at the center of your numerical cell, this point I, j, k. The vector potential instead is stored on the edges of the cell. For example, Az is stored on these edges of your box. The magnetic field that you actually evolve is the one that instead is stored on the face, as represented in this diagram. This was the staggered formulation means. So the vector potential is not stored at the center of the cell, but on the edges. The advantage to do this is something that we showed already in our first Spritz paper, Chocolate et al. 2020, and where we did a comparison between the evolution of the vector potential staggered, where a vector potential is located at the edges of the cell, with respect to a formulation in which instead you store the vector potential at the center of the cell. In Whiskey MHD, the code that developed in the past, for example, the vector potential was stored at the center of the cell. And that was done because at that time in carpet, it was not possible to have a staggered variable. Now instead it's possible, and so one can also use a staggered formulation. Something that I really noticed when I used the Whiskey MHD is that if the vector potential is stored at the center of the cell, essentially you may see the appearance of some oscillation, especially in the presence of shock. And this is something that we also saw with Spritz. For example, in this paper, what we did, we tested the standard version of Spritz, where the vector potential is staggered, and this is represented by the red line. The plot, by the way, is showing the value of the Y component magnetic field as a function of position for one of the Balzara tests, so one Riemann problem. So the black solid line is the exact solution, computed with my exact Riemann solver. The red one is Spritz with a staggered vector potential, which is what we will use. And then just for comparison, we also tested it with a vector potential which was not staggered. So a vector potential which is instead centered at the center of the cell. And in that case, which is the blue line, you see the appearance of some oscillations after the shock. There is a shock wave, and you see some oscillation in the blue line. You have a zoom here. This is not an instability, so this oscillation don't grow in time, but they are present. So in Whiskey MHD, what we did, for example, was to apply some Kresoliger dissipation to the vector potential, and this will get rid of this oscillation in magnetic field. But if you use a staggered vector potential formulation, this oscillation don't appear at all, so you don't need to use any Kresoliger dissipation. So this is something that I find very interesting about the difference between a staggered and non-staggered formulation. When you evolve the vector potential, you need to compute the electric field, and there are two different approaches. Both of them are implemented in Spritz. One approach is called flux CT, where CT stands for constraint transfer, and this is the same approach that was used in Whiskey MHD. A more recent approach that we implemented in Spritz is called upwind CT, and it is very similar to the one that is implemented in MHD. There is just a slightly different way in which the electric field is computed by the same method. So in a flux CT approach, one takes advantage of the relation that exists between the electric field and the fluxes of your conservative formulation. These relations are listed here. The electric field, in principle, lives on the edges, and in the flux CT approach, to compute the electric field on the edges of the cell, what you do, you just interpolate essentially the fluxes that share that edge. To make an example, here at the bottom, you see the expression to compute the Y component of the electric field in this point. And to compute this, you just take the flux along the Z direction on this phase here, the flux on the phase on the right here. These are the two fluxes there. The flux along the X direction, so on this phase here, and the flux in this phase. Okay, so these are the four phases that share this edge. And this way you can compute the electric. Okay, so you compute the flux, for example, by using HLLE for the magnetic field, and then you average essentially these fluxes in order to get the electric field. And then you use the electric field to evolve the vector potential with the expression that I did here. So this is the flux CT approach. Is the one that was implemented in Whiskey MHD, and the first one that we also used in Spritz. Then later we decided to switch to the upwind CT approach, which is described in many papers. For example, in this paper by Mignone and Delzana 2021, you can find a very good description of the method, as well as some tests comparing these methods with other methods. And in this case, instead of computing the electric field from the fluxes computed at the phase, what you do, you compute the electric fields directly from the velocity and the magnetic field. In ideal MHD, indeed, there is a relation between the electric field, the velocity of the fluid, and the magnetic field. In particular, electric field is just equal minus the cross product between the velocity and the magnetic field. Since the electric field is still stored at the edges of the cell, while the dynamic quantity, for example, the velocity is stored in the center, What you need to do is essentially to reconstruct the values of your different quantities at the edges. The magnetic field by construction is stored at the faces. So in that case, you just have to reconstruct it once in order to get the value of the magnetic field at the edge. For the velocity, for example, instead of you first have the velocity reconstructed at the face, and then after you have the velocity reconstructed at the face, you further reconstruct it toward the edge. This is essentially what happens in this case. So essentially, you reconstruct the magnetic field as well as the velocity toward the edge using your standard reconstruction method. Could be min mode or ppm in the case of Spritz, but could be any other reconstruction method. And after you reconstruct the value of the magnetic field and the velocity at the edge, you compute the electric field via this relation. This is essentially the idea between the city approach. Saying this way looks pretty simple, but the implementation takes some time. Why we did that? Well, already, if you look at the paper by Mignone and Del Zanna, there is some evidence that the flux city approach can suffer sometimes of the presence of some spurious numerical oscillation. For example, the plot you have on the left is from the paper of Mignone and Del Zanna, when they show the magnetic energy on the equatorial plane for the field loop advection test. On the top, you have the flux city approach, and on the bottom, you have the upwind city approach. And you can see that in the flux city approach, there are some spurious magnetic field in the field zone, while the upwind city doesn't seem to present any kind of spurious magnetic field. In Spritz, to be honest, we never saw with Fluxity any problem with this kind of test. The problem that we saw with Spritz when using the Fluxity was mainly when doing binary star simulations, in particular after merger. This is a figure produced by Lorenzo Inoggi some time ago, in which you compare the normal, the magnetic field, after the merger of equal mass binary star system. And what you have here is the normal the magnetic field on the equatorial plane or the orbital plane. So here is after merger, so you have the formation of hypermass neutron star that is here. You don't see it here because you just see the magnetic field. And on the left, you have the upwind city approach. On the right, you have instead the flux city approach. Well, for example, you see the formation of spurious magnetic field here, here, and here, and here. These are actually also quite close to the refined boundary. If you use the flux city approach and you don't want this spurious magnetic field to appear, then of course you can still add some Kreis-Holliger dissipation, but then I mean you miss on the advantage of using a staggered formulation. So both of these simulations don't use any Kreis-Holliger dissipation. If you have to run the constraint, the flux city approach with Kreis-Holliger dissipation on the vector potential, you will not see this spurious magnetic field. In the case of the upwind city scheme, even without Kreis-Holliger dissipation, you don't have any spurious magnetic field appearing. Let me also stress, I don't know if you can see the color bar, but here we are looking at 10 orders of magnitude in magnetic field strength. Okay, so this green is actually, it's several orders of magnitude below the magnetic field inside the star. So the color bar has been chosen in order to highlight the effect of this spurious magnetic field appearance. But this is essentially why we switched to upwind city. More recently, thanks to the work of Jay Kalinani, we also implemented the Spritz a very robust recovery scheme, which is called reprimand. This is also used by other codes. I think Jay also mentioned it during his talk on Monday. And the point of this conservative primitive scheme, reprimand, that is incredibly robust. As Jay said in his talk on Monday, essentially there are different techniques to compute the primitive variables from the conservative variables. There are techniques for which you need an initial guess. You also need to compute some derivatives. For example, the schemes that use Newton-Raphson method. Or you can have schemes that instead don't require an initial guess and are essentially based on bracketing the solution. And these reprimand schemes belong to the second category. It doesn't require an initial guess, and in particular is incredibly robust. For example, here on the right, you have an evolution of a magnetized neutron star with the magnetic field in this case also extending for a neutron star. So with color here, you have the strength of the magnetic field. Now, so this is the surface of the neutron star, and the magnetic field is at the polar configuration with the magnetic field extended also outside the neutron star. As you see, during the evolution of time, the structure of the magnetic field remains quite constant. If you try to evolve this system with a different conservative primitive scheme, for example, in Spritz, we have a scheme that was developed by Scott Noble, This solve a system of two equations with the Newton-Raphson scheme. In this case, soon after starting the evolution, we essentially, if you see, if we start to have problems, particularly near the surface of the star, you can compare this snapshot with this one. This is the same time, 0.1 millisecond after the evolution. If we increase the value of the artificial atmosphere outside the star, in this case, we increase the value of the artificial atmosphere by factor 100, then the Nobel scheme doesn't have any problem in recovering the correct values for the primitive variable. So it's really a problem that appears when you have high level of magnetization, so ratio of magnetic pressure to gas pressure, or you prefer magnetic energy density on gas or as mass energy density. In the case of reprimand, they really deal without any problem with very large values of magnetization. Very recently, we also started to do some tests of Spritz with binary star system, both with ideal fluid equation of state as well as piecewise polytropic equation of state. This is work that is mainly been done by J. Calinani, who is there with you at Rochester. These are some snapshots, for example, the evolution of a binary neutron system with neutron star both 1.5 solar masses. This should be the same system that people typically call the missing link system. So these are Lorentz, standard Lorentz initial data. As I said, another fluid equation of state was used in the evolution. This run was using a quite coarse resolution on the finest grid, but then more refinement levels were added just before the collapse of the core after the two systems merged. In this simulation, what we do is to add the magnetic field after two orbits, or if you prefer, essentially one orbit before merger, and it's a dipolar magnetic field extending also outside. This is something similar to what has been done also in other simulations, for example, by Illinois, with Illinois GRPG, an example. And the maximum value of the magnetic field tends to 16 Gauss. So as Carlos Valenzuela pointed out, this magnetic field is not realistic, but since in our case, we cannot really resolve the small scale turbulence scales that led to such a strong magnetic field amplification, we start already, as done by other people, with a large magnetic field. Something particular that we do, and then when we add the magnetic field, we also modified essentially the matter outside the neutron star, if you want, the atmosphere outside, in order to put the material co-rotating with the neutron stars. The reason we do that is because we use ideal MHD approximation, and the ideal MHD approximation, the fluid essentially is frozen with the matter. In our artificial atmosphere, we set the velocity to 0. So if we weren't putting the matter co-rotating with the binary, then the magnetic field lines outside the neutron star will be frozen in the frozen atmosphere, let me call that way, and this will strongly distort the magnetic field. So we decide to create essentially a co-rotating atmosphere around the star in order to reduce essentially the perturbation to the initial configuration and magnetic field line. And this is a plot by J, which shows essentially the angular velocity is a function of radius. This before adding this co-rotating material, and this after the addition of the co-rotating material. And the co-rotation is chosen by following essentially a Keplerian profile. These are some movies. On the left, you have the rest mass density, and on the right, the norm of the magnetic field. The top panel shows the evolution on the XZ plane, and the bottom panel on the equatorial plane. Let me play them again. So you will see the neutron star orbiting around each other for 3 orbits, then they merge, they produce an hypermassive neutron star, and then collapse to a black hole surrounded by an accretion disk. You also have a low density panel on the vertical axis, but unfortunately, at the end of the simulation, we were not able to see the formation of a relativistic jet. This is the movie starting again, and you notice from the right panel, the magnetic field is not present in the beginning, but it's just after one orbit before merge. Okay, so nothing, and then it's at just one orbit before merge. So these are just the final snapshot. So as I said, you have a black hole surrounded by an accretion disk. There is a low density panel, but unfortunately, in this scenario, we didn't see the formation of a relativistic jet. More recently, we started to do simulation with piecewise polytropic equation of state. In particular, J ran some simulation with the APR4 tabulated equation of state. And in this case, it's something that is very nice, and that we see that 50 milliseconds after collapse to black hole, more or less 50 milliseconds after collapse to black hole, a jet is actually launched. So we see a region that is magnetically dominated within the funnel that I was talking about before. So for example, in the left panel, you have the configuration of the magnetic field lines at the end of the simulation. This was 100 milliseconds after merger. This vertical black line has a scale of around 500 kilometers. So the black hole and the disk are really here in the center. And you see that the magnetic field is very well collimated. There's this sort of a colloidal structure aligned with the spin axis on the black hole. The central panel instead shows the ratio of magnetic energy density on the rest mass energy density of the fluid. And you see that this funnel, so the black hole will be here at the center, the disk will be here. The funnel above and below the black hole is strongly magnetized with a ratio that reaches even a factor of 100 or a bit larger than that. And here on the right, instead, you have the velocity profile of the matter, and blue essentially means outgoing flux of matter. So essentially in this region, you have matter that is expelled from the system. So we have the formation of a jet, and it's a jet that can potentially reach a Lorentz factor of order larger distance from the center. So to conclude, is the question, Spritz is a new publicly available code that can work with magnetic field, find a temporal tabulated equation of state, and can deal with neutrino emission. The code is publicly available. In particular, the version that is publicly available on Zenodo is the one that is described in the paper that we published in 2020-2021. There is a new version with Spritz, which is not yet publicly available, that includes the new upwind city scheme to allow the vector potential instead of the flux city approach, and includes also the use of the Riemann conservative primitive scheme that allows us to evolve neutron star binaries with external dipole field without encountering any failure in the conservative primitive. And as just shown, we have some simulation in which we finally see the formation of jets. We have to start with quite strong magnetic field since the beginning, but it's something that is very common in this field. And as I said, and as Carlos mentioned yesterday, it's mainly due to our lack of resolution during merger in order to be able to follow the strong magnetic field amplification we expect at merger. So hopefully we will present these results in a paper very soon. So stay tuned, and this is just the QR code that points to the Zenodo repository. Thank you very much for your time, and let me know if there are questions.
So thank you, Bruno. We do have some time for questions. So if anyone has a question, feel free to ask.
Should I go there?
Yeah, you can come up here, or that was the easiest.
Bruno, can you hear me?
Yes.
All right. I have two questions, if that's great. So the first one is, I was wondering if this formulation of the vector potential conserves the magnetic flux across the refinement, the mesh refinement boundaries. And if you have any diagnostics of that in your tests.
This is an excellent question. So at the moment, not yet. So there are concerns that indeed by evolving the vector potential, you may not conserve the magnetic flux. I have our collaboration right now together with Philip Mosta and the group of Team Dietrich. They also developed their own MHD code to run some tests. Also, the collaborations include the group of Masaru Shibata, so in particular Kentucky. So the idea is to run some tests between these different codes. So my Spritz code, the code by Philip Mosta, the code by Masaru Shibata, and the new code by Team Dietrich, which include, for example, some tests like, for example, the cylindrical explosion or the spherical explosion, including mesh refinement, in order to check for the conservation of the magnetic flux when you cross the refinement boundary. So this is something on which we are going to work on and have a look. But we didn't do any specific test just yet. But we are going to do that as part of this collaboration with the different groups in order to do a counter comparison and see how good we can evolve in the magnetic field.
See, cool. And the other question I had is, with this new contour prim that you have, you can basically evolve these highly magnetized regions robustly, right? But I was wondering if you get a solution there, but is it close to the force-free solution? Do you have a way to to compare with what you get in like true force-free magnetosphere environment?
Oh, I don't know about that. I don't think we did a comparison with a force-free. I mean, if J is there, of course, J can also correct me, but I don't think we did a comparison with a force-free scenario.
All right, thank you.
Thank you very much.
Any other questions for Bruno?
Maybe I ask one. Where is that? Hey, Bruno, very nice talk and very nice results. I have one question on your simulation where you see jet launching. This was, from what I understand, also where you put the magnetic fields initially outside of the stars.
Yes.
Do you have any diagnostics in the simulation of how much colloidal flux is left from your initial condition, or does that just get accreted at later times? Or basically, I'm wondering, do you have any insights on how the magnetic field from the beginning translates to aiding the jet launching?
Oh God! So in principle, we have diagnostic to track the amount of colloidal and toroidal components in magnetic field. But for this scenario, I don't remember because we focus so much on the jet formation that personally I didn't have a look at that. The simulation are done by Jay, so this is another question. Sorry, that maybe you can ask Jay. But yeah, I don't remember. I didn't have a look at this. But we have a diagnostic to track. I mean, how much of colloidal field we have.
Yeah, just to comment on that, we haven't looked at it yet, but that's a good thing to follow.
Thanks.
Any other questions for Bruno? I have just a quick question, Bruno. So the mass that you add on the outside, does it have a spherical distribution, but then a kind of a Keplerian profile in the velocity? Is that correct? For
So this R is the cylindrical radius, so the radius with respect to the z-axis.
Okay.
I don't know if this answers your question or.
Yeah, I think that does.
Okay.
Okay. Well, thank you, Bruno, for your presentation.